everyone. Today I'm going to analyze a machine learning workflow designed to predict liver cirrhosis stages using the Mayo Clinic PBC clinical trial dataset. The core objective of this project is to evaluate a binary classifier that predicts whether a patient has reached stage 4, the most advanced level of the disease. So, as seen in the implementation, NumPyWare was used to collapse the original 4 stages into a binary target. This approach effectively aligns the model with the real-world clinical urgency of identifying high-risk patients. Looking at the data pre-processing section, the workflow goes beyond basic cleaning by applying several sophisticated statistical techniques to reduce noise. For instance, the script drops irrelevant identifiers and handles missing values for key metrics like albumin and globulin ratio. To address the long tail distribution common in medical data, log 1p transformation is applied to screwed features such as Brilliant, and this step is crucial as it normalizes data, which significantly optimizes the performance of linear models like logistic regression. And the workflow also manages outliers through two-key rule and winsorization, capping extreme values between the 5th and 95th percentiles. And this maintains the integrity of the sample size while preventing extreme data points from distorting the model's gradients. Furthermore, to address the class imbalance where stage 4 cases are the minority, the code implements mode to generate synthetic samples, ensuring the model isn't biased towards a majority class. So, regarding the validation strategy, the notebook follows rigorous machine learning protocols. Establish a 80-20 train test split as a holdout set for final evaluation. Within the PyCaret setup, a 5-fold cross-validation is utilized, and the importance of this method cannot be overstated. It ensures that the model's performance isn't just a result of a lucky data split. By rotating through different folds, the workflow provides a stable estimate of how the model generalizes to unseen patients, and proving whether it has captured actual patterns or merely memorized the training set. A critical part of this analysis is the bias variance trade-off seen in the model comparison. Notebook evaluates logistic regression alongside the tree-based models like random forest. Logistic regression, being a linear model, tends to have high bias because it assumes a simpler relationship than what might actually exist in a complex clinical data. Conversely, a single decision tree can capture nonlinearities, but often suffers from high variance, leading to overfitting. And the choice of random forest in this workflow effectively balances these two. By using an ensemble of trees, the model retains low bias while significantly reducing variance through averaging. And the confusion matrix in the results provides clear evidence that this ensemble approach is much more robust for clinical feature sets. Finally, we can draw several insights regarding real-world applications. In a clinical setting, recall is often prioritized over accuracy because missing a stage 4 diagnosis, a false negative, carries much more higher risk than a false positive. And these visualizations, specifically the heat map and classification reports, demonstrates that model is high sensitive in flagging stage 4 cases, largely due to the pre-processing and smooth strategies. In a practical scenario, such as a workflow, could be integrated into diagnostic systems to act as a second set of eyes and flagging high-risk results for immediate physician follow-up. Overall, this implementation of visualization and random forests demonstrates a well-rounded approach to building a model with linear clinical unity. Thanks for watching.